This is the second part of reaction classification and prediction. In this video we will look at decomposition and synthesis, followed by combustion type reactions. Okay, we'll go back a slide. We're going to look at decomposition first. With decomposition reactions, we're going to have a compound break into simpler substances. This could be elements, compounds, or combination. So generally we would have something like compound AB breaks apart into A plus B. So decomposition is exactly what it sounds. It is going to be the breaking apart, or decomposition literally means breaking apart of something. So in our first type of reaction, we're going to look at binary compounds. Binary compounds are made of two elements, and when they decompose, that compound is going to break apart into its elements. So for instance, if A and B are elements, then compound AB breaks apart into the elements A and B. So as an example of that, we can have water decomposing, H2O decomposing. Notice that in this reaction, as compared to the first two, which were single replacement and double replacement, that we only have one substance to the left of the yield arrow. This one substance, there's really only one thing that it can do, which is break apart into hydrogen and oxygen. Okay, this would be liquid water, hydrogen gas, oxygen gas. And this does need balancing. We would have to have, we've got two oxygens versus only one, so we place a 2 here and then a 2 in front of hydrogen. Another example would be mercury 2 oxide, which is HgO, decomposes. This is an ionic compound, so it would be a solid. This requires an energy source, the same thing for the water on the previous slide. So usually this would be heated strongly, and it's going to produce mercury, probably in the liquid form, and oxygen gas. We've got 2 oxygens versus 1, so we need a 2 here and a 2 here. And our next reaction type would involve metallic carbonates. So we would have a metallic, where M is standing for metal or metallic, carbonate. Metallic carbonates break apart when they're heated into a metal oxide plus carbon dioxide gas. So as an example, magnesium carbonate, which is a solid, if it's heated strongly, it will break apart into magnesium oxide, which is also a solid, plus carbon dioxide gas. And it's actually balanced as it's written. Sodium carbonate is a second example, Na2CO3, solid, heated, would break apart into metal oxide, Na2O, plus carbon dioxide gas. Again, it's balanced as written. This would be a gas, this would be a solid. So the next reaction type is the decomposition of a metallic hydrogen carbonate, This would be a metallic hydrogen carbonate. These would decompose on heating to produce a metallic carbonate plus water plus CO2. So for instance, sodium hydrogen carbonate is going to produce NaHCO3. It's just baking soda. If heated, produces sodium carbonate plus water plus CO2. So we've got one, so we need two here. That gives two hydrogens, two carbons, two carbons, and six oxygens. That's 3, 4, 5, 6 oxygens, balanced as written. Calcium hydrogen carbonate decomposes according to the same pattern, which is going to be calcium carbonate plus water plus CO2. And here we've got one calcium, two hydrogens, two carbons, 6 oxygens, 3, 4, 5, 6 oxygens, all balanced. Metallic hydroxides decompose to produce a metal oxide plus water. As an example, magnesium hydroxide, MgOH2, decomposes, if heated, to produce magnesium oxide plus water. And that's balanced as it is written. A copper 2 hydroxide decomposes when heated to produce copper 2 oxide plus water. And again, it's balanced as written. Metallic chlorates have a tendency when heated to decompose into metallic chlorides plus oxygen gas. So something like lithium chlorate, LiClO3, will decompose into LiCl plus O2. Need a 3, a 2, and a 2 to balance that. Potassium chlorate decomposes when heated to produce potassium chloride plus O2. Same pattern in balancing as the previous problem. Decomposition of oxyacids. So an oxyacid is, first of all, is going to be an acid with a polyatomic ion, such as H2SO4. And the way these are going to decompose is we're going to have hydrogen, first of all, a non-metal, so X equals a non-metal with oxygen. This is going to decompose into a non-metal oxide and water. So as an example, I'm going to change ink colors. As an example, phosphoric acid, H3PO4, when it decomposes, has a tendency to break apart into a non-metal oxide. The non-metal is coming from the polyatomic ion, the non-metal other than oxygen. So that's going to be a phosphorus oxide plus water. The phosphorus oxide has an issue, though. Phosphorus has multiple oxidation numbers, so we don't know what the charge of phosphorus is here. The oxide we know is going to be a -2. So we've got a problem that we don't know the oxidation number of the phosphorus. But we can say, in most cases, all the cases that you're going to see, that the nonmetal from reactant to product retains its same oxidation number. So the phosphorus does not have a change in oxidation state. So if we can come to H3PO4, and we know hydrogen is a +1, we know oxygen is a -2, if we call X phosphorus, or the charge of that, then we know that 3 times 1 is 3, plus X, minus 4 times -2 is -8, equals 0, because compounds add their oxidation numbers up to 0. We solve this. This is a -5 plus X equals 0, so X equals 5. So that means phosphorus has a charge of +5. Now, if we write the formula for that, that's going to be P2O5. So I'm just crisscrossing here. So rewriting the equation, H3PO4 decomposes to P2O5 plus H2O. And this does need to be balanced. We've got, I want to put a 2 here and a 3 here to balance the hydrogens, to give a common multiple of 6. That gives 8 oxygens. 2 times 4 is 8. And then we also have 2 phosphorus, so that's balanced. Final answer. Let's try another of those. That's sulfuric acid, H2SO4. The sulfur, this is our nonmetal that's going to produce the oxide. So that's going to produce SO and water. But our SO, we don't know the subscripts, so we need to find our subscripts for those. We know that the oxygen is a -2. Sulfur is the X. It has multiple possibilities. So when we go to H2SO4 to find the charge of sulfur, sulfur is our X, oxygen is -2, hydrogen is +1, so 2 times 1 is 2, 1 times X is X, 4 times -2 is -8, equals 0. Solving for X, X is going to equal 6. So this oxidation state is 6. So that becomes S2O3. Reduce this. Oh, that should be O6, by the way. We'll reduce this by dividing each of them by 2. And that's going to be SO3. So we have H2SO4 decomposes to SO3 plus H2O. And you can see with this that it makes sense if we pull a water out of this. It doesn't always work out this way, but it does with this particular one. If we pull a water away from this, take 2 hydrogens and 1 oxygen, that leaves an SO3 behind. That's the final answer. Okay, so our next reaction type, actually we can do another of those because they are a little more difficult. So nitric acid, HNO3, is going to break apart into an NO, which we don't know subscripts on those, plus water. And with the N, that's going to be our X, -2 on the oxygen, HNO3, we got +1, X, and -2 on the hydrogen, nitrogen, and oxygen. So that's going to be 1 plus X, because we've got 1X, we've got 1 +1, minus 6 equals 0, X equals 5. So that means phosphorus is 5. So that gives HNO3, breaks apart into N2O5 plus H2O. Final answer. All right, let's look at decomposition of hydrates. You've got some experience with these. They're very easy. So barium chloride dihydrate. When we heat these, as we've seen in lab, we're going to separate it into the salt and water. And it's just that simple. That's the end result. Magnesium sulfate, heptahydrate. This is Epsom salts. We heat this, we produce magnesium sulfate and 7 waters. Peroxides are also fairly common substances to decompose. Peroxide is O2 with a -2 charge, meaning that each individual oxygen has a -1 oxidation state, but it comes as a polyatomic ion as O2. So for instance, hydrogen peroxide is H2O2. Hydrogen peroxide decomposes. Actually, this one decomposes by light. It's the reason hydrogen peroxide is sold in brown bottles, to block the light that causes it to decompose, and it will separate into water and oxygen gas. That's really the only peroxide that you need to worry about knowing about. This is a fairly common one. You can if you buy peroxide and you keep it well beyond the expiration date, then very often what you end up having is this. You can also see that if you keep peroxide for a long time and the bottle stays closed and tight, that it may be swollen, and the reason for that is that you've got oxygen gas that has escaped into the bottle and causes the bottle to expand, possibly to the point of rupturing or breaking the lid off the bottle so that the oxygen actually escapes to the outside. All right, let's take a look at synthesis. Synthesis, for the most part, is opposite decomposition. So with synthesis, the simple synthesis reactions are going to be things where we have simple components yield more complex, such as A plus B yields AB. Two simple things are put together to make them more complex. A and B can be elements or compounds. All of ours are going to give single product. So one type of synthesis reaction that you want to be familiar with is hydrogen plus a nonmetal. So in that case, we have hydrogen gas plus chlorine gas, and this is going to be hydrogen gas plus nonmetal. It's going to be an acid, and this acid is going to be binary. So H2 plus Cl2 is going to yield HCl. Fairly simple. Hydrogen gas plus iodine vapor, I2, is going to yield hydroiodic acid. And again, we need a 2 there. Don't forget the diatomic hydrogen and iodine. Metal-nonmetal reaction. So metal plus a nonmetal yields an ionic salt. With the metal is going to be the positive, the nonmetal is going to be the negative portion of that. So if we have something like sodium plus chlorine gas, that's going to yield NaCl, salt. And we would have 2 to balance the chlorine, and we need a 2 in front of the sodium. Calcium plus oxygen gas is going to yield calcium oxide, which is the salt, the ionic compound. CaO is the proper formula, so we need a 2 to balance the oxygen and a 2 to balance the calcium. Metal oxide plus water. Metal oxide plus water is the opposite of decomposition of an oxyacid. Oh, this is a metal oxide, excuse me. It's not going to produce an oxyacid. It's going to produce a metal hydroxide. Which is actually a base. So if we have calcium oxide plus water, these nonmetal oxides, by the way, are sometimes called basic anhydrides, which just means a base without hydrogen. So we put these together and we're going to make calcium hydroxide, CaOH2, and it's balanced. And sodium oxide plus water, Na2O plus H2O, is going to yield a metal hydroxide. Sodium's the metal hydroxide. And we do need a 2 here to get 2 sodium, 2 hydrogen, 2 oxygen, 2 sodium, 2 hydrogen, 2 oxygen. Okay, nonmetal oxide, which is an acidic anhydride, plus water, is going to yield an oxyacid. So if we have dinitrogen tetroxide plus water, we're going to have an oxyacid. Oxyacid is going to have hydrogen from the water, a nonmetal other than oxygen as part of a polyatomic ion. Let's make this, I believe this is going to give a bad result. Let's make this pentoxide. And this becomes HNO3. That should be 5. And to balance this, we're going to have a 2 here. This is a 5, so that's 6. That's balanced. Carbon dioxide plus water, CO2 plus H2O. This is going to yield H2CO3, carbonic acid, and it's balanced. Sulfur dioxide plus water is going to yield H2SO3. Put it all together. Okay, next. Synthesis, we have synthesis reactions are the opposite of decomposition. So if we have something like carbon dioxide gas plus sodium oxide, this is the opposite of the decomposition of a metallic carbonate. So that's what we're going to produce. These would be the products of the decomposition of a metallic carbonate. So in this case, we're going to combine them and we're going to produce Na2CO3. So metal oxide plus carbon dioxide gas produce metal carbonate. And I believe we are balanced. Calcium chloride plus oxygen gas. These are the products of the decomposition of a metallic chlorate. So we're going to make a metallic chlorate. We're going in the opposite direction, so this would be CaClO3. And finally, we arrive at the last type of reaction, which is the combustion reaction. Combustion means to burn in oxygen. And these always take the same form. We're going to have these are all going to be carbon compounds. And they always take the same form. We have our original reactant, which is the fuel, the carbon compound. This is C6H12O6. Burns in oxygen, O2. The products, CO2 plus H2O. Now, all of our combustions are going to be a carbon and hydrogen at least. We can also, though, have, like this, a carbohydrate, where we've got oxygen, but we still end up producing the same products. You'll notice here that if we've got, really the only thing that's changing is what's being burned. So this is an easy one to remember. And we've got ethanol, C2H5OH, burns in oxygen, and the products are going to be CO2 plus H2O. So over here I've got 5 plus 1 hydrogen. I'm going to put a 3 here for that. I've got 2 carbons, so I'm going to put a 2 there. That gives me 4 oxygens plus 3 is 7 oxygens. Let me write that down on this side. And over here I've got 2 plus 1 is 3. So I'm going to subtract, I'm just going to take away that 1. That means I've got 6 more to go. And that would be it. So that would give you 6 plus 1 would be 7. So 2 carbons, 2 carbons. 5 plus 1 is 6 hydrogens. 3 times 2 is 6 hydrogens. And we've got 6 plus 1 is 7 oxygens. 4 plus 3 is 7 oxygens. Propane, C3H8, burns in oxygen. O2. CO2 plus H2O. Okay, I've balanced that, but I also notice that as I do this, each of these coefficients is divisible by 2, so I started with the wrong exponents. I can reduce them and say C3H8 plus 5O2 yields 3 CO2 plus 4 H2O. And that would be a balanced equation. That takes care of all of our reaction types. You'll be getting some practice on identifying the reaction types as well as predicting products following the video.